Hello everybody. So in this video we're going to discuss one new topic which is related to what we covered before, which is the mass balance for reactive systems. And in this video we are going to discuss one very common thing that happens in reactive systems for multi-unit systems, which is something happens in real processes. And to understand what is this point, we will discuss this flow sheet that we see here. So we discussed this flow sheet before, but I want to go into more details here. So in this flow sheet we have hydrogen and nitrogen with the flow rates given here, and this is the feed to the reactor, where the reaction between hydrogen and nitrogen takes place as it's written here, producing ammonia. And this is the product stream. It's hydrogen, nitrogen, and ammonia. The conversion of hydrogen or nitrogen, I'm sorry, is almost 33%. So we have 300 moles in. This is nitrogen, I'm sorry. This is 300 moles in, and only 100 are converted, which is one third of the nitrogen fed. And then we have 200 moles out with 400 moles of nitrogen and 200 moles of ammonia left. And this is the desired product. So what we do is we separate the products this stream into two different streams. One of them is very rich in ammonia with traces of hydrogen and nitrogen, and the other is very rich in hydrogen nitrogen with traces of ammonia. So this is what we see in this flow sheet. And we have a lot of hydrogen and nitrogen that are unreacted here, and we didn't make use of them, or we couldn't convert them to ammonia because the conversion of the conversion of nitrogen in the reactor is very limited. It's only 30%. So I will definitely have more unreacted hydrogen than the produced ammonia, and nitrogen, of course, than the produced ammonia. So this is if I keep the flow sheet as it is now, then these are going to be wasted resources. And we discussed before how can we make use of these wasted resources. Instead of just getting rid of them, we can recycle these components. And by recycling this stream, what we do is we make sure that the unreacted hydrogen nitrogen are going to go again into the reactor. And as they go into the reactor, they will pass by the same conditions again, and the reaction is going to proceed. The beautiful thing about the recycle stream is that you will always have the unreacted hydrogen and nitrogen going back to the reactor through this closed loop, and all or most of the ammonia that is produced is going to be produced here. So with the recycle stream, I'm not changing the conversion of the reactor. It's going to be affected, of course, because there is some ammonia that were coming here in the top product are now recycled back to the reactor. So we have some ammonia going in that may change the conversion. But let's say the conversion is still 33% in the reactor. The overall process is much more efficient. So the efficiency here is only 33%, but the efficiency of the whole process with the recycle stream is way higher than before. So we can still, with the separator, we can still keep the ammonia concentration here to be, let's say, 95% or whatever. Okay, so we'll have high purity ammonia here because of this separator. But the point is, if we look at the unreacted hydrogen and nitrogen here compared to the hydrogen nitrogen in the feed, this would be very small amounts. So in the previous case, when we looked at the flow sheet, we had almost 60% of the hydrogen nitrogen that were not converted. So we have the conversion at 66%. 33%. But now with the recycle stream, if you look at the whole process, we just consider what's going in and what's going out of the process, you'd see that the conversion can be more than 90%, which is a very big improvement in the conversion. So the conversion that was only 33% in the reactor increased too much by recycling the unreacted components into the reactor, and the overall conversion, or the conversion of the overall process, or the efficiency of the whole process, increased to more than 90%, which is a very, very, very big improvement in the performance of the process. So this is why we have to distinguish between two different terms now, which are called the overall and single pass conversion. Before I discuss the difference, I just want to demonstrate what we mean by a single pass. So here we have hydrogen, nitrogen going into the reactor. So they pass by the reactor once, and some of them are not reacting, and this is what we know. It's not some, it's most of them are not reacting. It's 66% is not reacting. So we will have here a lot of hydrogen, nitrogen that didn't react. They are going to return back to the in the recycle stream to be mixed with the fresh feed, and then to be the reactor feed. So they will pass by the reactor one more time, and they can pass by the reactor 3, 4, 5 times until they get consumed by the reactor. So what we mean by a single pass conversion is the conversion that takes place in one pass. The conversion, the conversion which is calculated from this stream and this stream by just one pass. We don't consider going back and forth many times. If it goes once, what would be the conversion? This is what we mean. So the conversion is still conversion. So it is the number of moles in minus number of moles out over the number of moles in. This is the definition that we know, and we have already used it many times. But for to distinguish between these two terms, the single pass conversion is the conversion that is a single pass, as we define the single pass. So it is the number of moles into the reactor minus the number of moles out of the reactor over the number of moles into the reactor. The overall conversion is going to be concerned with the whole process. So it's the number of moles into the process minus the number of moles out of the process over the number of moles into the process. So if we want to write this in the form of equations for hydrogen, for example, it's going to be, the single pass is going to be the number of moles of hydrogen into the reactor, which is stream number 2, minus hydrogen in stream 3 over the hydrogen in stream 1. The overall conversion of hydrogen, it's the number of moles of hydrogen in stream 1 minus number of moles of hydrogen in stream 5 over the number of moles of hydrogen in stream 1. So this is the single pass and the overall conversion for hydrogen, and the same for nitrogen. It's the same, it's nitrogen instead of hydrogen. So it's the exact same thing. There is one thing that I want to mention here, which is an important point. It's not related to mass balance, but it's a good thing to mention within this context, because it's very related. So it seems that the recycle is very useful, and it improves the performance of the process very much compared to the process without the recycle, which is true. But there are some consequences to having this recycle stream, and these consequences will have impact on the process and the economics of the process. We don't discuss economics here, but it's something, again, this is something just for your knowledge and to be aware of this thing. So we draw here a stream that is going back, which is stream number 4, and in order for the process or for this stream to be able to go back from this separator to the mixer, it needs compressing or pumping, which requires equipment for this, a pump or a compressor, and it requires electricity for operating this equipment. So it costs money for this, which was not before. We didn't have to do this before. Also, the equipment size for the reactor and the separator, it's in the beginning it was without the recycle, it was designed to operate on 1000 kilomoles per hour. Now it can be 2000 or maybe more. So it's doubled or more than doubled. So this will require larger reactor size and larger separator size, which will also lead to more cost for the equipment cost, and more cost for operation, because you would need more energy. If you want to heat this reactor, you would need more according to the conditions of the separator. But anyways, so this is the cost that we pay for recycling the streams, and in return this cost would be paid off by increasing the product flow rate. So this way we are producing more ammonia, and this would be the reward that we get for this recycle stream. So I'll stop here, and in the next video we are going to solve an example on this. So I'll see you then. Goodbye.